everyone. They will practice with the notion of independence. We'll work on two exercises, in the second of which we will practice with the extremely useful trick of conditioning. But let's recall the definition of independence first. By definition, events E, F, G, and H, for example, are called independent if we can compute the probability of intersection of any subset of them by multiplying their probabilities. For instance, probability that F intersection G equals probability of F times probability of G. Also probability E intersection G intersection H, for instance, equals P of E times P of G times P of H, and so on. Any subset of these events, such as F and G, or such as E, G, and H, is allowed. Independence is stable. For example, if you take events E and G and form any subset, such as E intersection G complement, that event will be independent of any event formed from the other subsets, such as F union H. Independence usually is denoted by the symbol that resembles orthogonality. And now let's practice. Example 1. A Boeing 747 looks like this. It has two engines on each wing. It can fly if at least one engine on each wing works. During a flight, an engine can fail with a very small probability. Let's call it P. Let's assume that engines fail independently of each other. Let's find the probability that the plane can fly. So we are interested in the probability of this event. Let's call it E. This event is determined by which engines work and which fail. So let's look at these events. EI will be the event that engine I works, where I can be one of these four engines, 1, 2, 3, and 4. The assumption says that the engine fails with probability P, and therefore it works with the complement probability, 1 minus P. So probability of EI equals 1 minus P. By assumption, the plane flies if at least one engine on the left wing works and at least one engine on the right wing works. At least one left engine works means engine 1 works, or engine 2 works, or both. The logical operation or corresponds to the union. The logical operation and corresponds to the intersection. And at least one right engine works means that E3 or E4 happens. So we expressed our event E just like this, and now we compute its probability. Because the engines fail or work independently, the events EI are independent, and so are the events formed of them by stability. So this event involves only E1 and E2, and it is then independent of this event, which involves the other two events. So these events are independent, and by the definition of independence, the probability of their intersection is the product. Let's compute each of these terms separately. How can we compute the probability of the union of two events? By inclusion-exclusion principle, it equals probability of E1 plus probability of E2 minus the probability of their intersection. P of E1 is this probability, P of E2 is this, and if we sum them up, we double count their middle part, the overlap, so we need to subtract it to correct double counting. Because events E1 and E2 are independent, the probability of the intersection is the product of probabilities. P of E1 is 1 minus P, P of E2 is also 1 minus P, and so we get this expression. If we simplify it, it will become 1 minus P squared. Do it. We computed this term. It is 1 minus P squared. Similarly, we can compute this term. In fact, the expression is exactly the same. Probability of E3 union E4 is also 1 minus p squared. So both of these factors are 1 minus p squared, and we get that the probability that the plane can fly is this, and that's the answer to the problem. Exercise 2. 4 towns, let's call them A, B, C, and D, are connected by 5 roads like this. On a snowy day, each road is open with probability p or closed with probability 1 minus p, independently of the other roads. Let's find the probability that on a snowy day, one can get from town A to town B. So we would like to compute the probability of this event that we call E. This problem can be tricky if you attempt to solve it directly. It is because there are so many different routes that you can take from A to B. You would need to be able to compute the probability of each such route and then take the union, because you would like to get from A to B by at least one route. The probability of the union, in principle, can be computed using the inclusion-exclusion principle, but it will have a lot of terms because there are so many routes. There is a simpler way to solve this problem using a trick of conditioning that we've seen once. Is there any information that might help us solve this problem? If we know the state of the road CD, whether it is open or closed, will that help? Yes. For instance, if we know that road CD is closed, then you can get from A to B only in 2 ways, like this or like this. And that simplifies the problem a lot. There is now only 2 routes. So the first and the principal step of the solution is to condition on the state of the road CD, whether it's open or closed. Then we use the law of total probability to compute the probability that one can get from A to B. It's P of E conditioned on the event that the road is open. Let's simply call that event CD times probability that the road is open, plus probability of E conditioned on the fact that the road CD is closed, that's a complement to event CD, times probability that the road is closed. Any road is open with probability P. And so this is P, and this is a complement of it, 1 minus P. Thus, the problem reduces to computing these 2 conditional probabilities. Let's do them, starting from this one. The probability that you can get from A to B if the road CD is open. So the situation we're looking now is this. We for sure know that the road CD is open. To get from A to B, then, you just need to get to the road. So if the road CD is open, the event that you can get from A to B can be expressed as both towns A and B are connected to CD. What's the probability that A is connected to the road CD? That means that either road AC is open, or road AD is open, or both are. Each road is open with probability P. So the probability of this is P. The probability of this is also P. And what's the probability that both AC and AD are open? That's the probability of the intersection of the 2 events. Both of them have to happen. These events are independent because they involve different 2 roads. So the probability of the intersection, by definition, is P times P, or P squared. Therefore, by inclusion-exclusion principle, the probability that A is connected to the road CD equals P plus P minus p squared, which is 2p minus p squared. We computed the probability that A is connected to the road CD. Similarly, we can compute the probability that B is connected to CD. And the probability would be the same, 2p minus p squared. So how do we compute the probability that both A and B are connected to CD if we know the probability of each? Here we use independence. A is connected to the road, B is connected to the road are two independent events because they involve different subsets of roads. A involves these two, B involves these two. So by independence and stability, this probability equals 2p minus p squared times 2p minus p squared. We computed this term. Next, compute this term. What's the probability that you can get from A to B if the road CD is closed? In that case, you can get from A to B in only two ways, via C or via D. So our event E, which is you can get from A to B, is equivalent to the route ACCB is open, or the route ADDB is open, or both. What is the probability that the route ACCB is open? For that, we need both roads to be open, road AC and road CB. Each is open with probability P, and they're independent. Therefore, the probability that both are open, the probability of the intersection of the two openness events, is P times P, or P squared. We can argue the same for this route. This probability is also P squared. And the probability that both routes are open, this and this, would require all four roads to be open. And the probability of that, by definition of independence, is P times P times P times P, or P to the fourth. Now, to compute the probability of the union, which is what the operation OR stands for, we will use again the inclusion-exclusion principle for these two events. So the probability will be the probability of one event, P squared, plus the probability of the other event, P squared, minus the probability of their intersection, which is P to the fourth. And that's 2P squared minus P to the fourth. At this time, we have computed all the four terms in the law of total probability. The first term is this, 2p minus p squared squared. The second term is here, 2p squared minus p to the fourth. And this is our answer. The probability of E equals 2p minus p squared times p plus 2p squared minus p to the fourth times 1 minus p. You can simplify this expression if you like, but that's the answer to our problem. The main step that allowed us to solve this problem was the trick of conditioning. The cue to apply conditioning is this. You can ask yourself, no, if there's anything, any information that could simplify this problem, then let's condition on that. In case of this problem, this information was the state of the road CD. If it's open, we can solve the problem. If it's closed, we can also solve the problem. And then we can combine the two using the law of total probability. We'll keep practicing with the conditioning trick in the next couple episodes. And one remark, the road network that we just analyzed is an example of a graph, which is generally a collection of vertices, towns, and edges that connect them. More specifically, in this problem, we looked at a random graph where each edge can be present or absent. Stay with me.